Okay, so next exercise 544. We have a positive real number x. We have to show that there is a positive integer n for which these inequalities are true. So in particular, this exercise shows that no matter how small x is, we can always choose a positive integer n such that 1 over n is still smaller than x, but at the same time, of course, positive. So let us see how the solution can be had. Since x is positive, the Archimedean property implies there exists a positive integer excuse me, n such that n times x is greater than 1. So we are applying the Archimedean property with the numbers x and 1, both of which are positive. So we know that we can choose a positive integer n such that nx is greater than 1. Then obviously, then using the laws of inequality that we already have proved for real numbers, we have these things. So that's it. That is the solution. Next, not many things are left in this set of exercises, so let's just try to finish this. Five, 4, 5. Proof proposition five, 4, 14. Hint is also given. Use exercise 544, that means the previous one. And also you may also need to argue by contradiction. Okay, so let us recall what the proposition 5414 says. It says that if we have two real numbers x and y such that x is less than y, then we can always find a rational number q in between x and y. That's what the proposition says. Okay. Now, how can we possibly find a rational number? We are again going to take the help of, we are going to start off with the Archimedean property. And we will have this: since y minus x is positive. This is coming from the hypothesis given to us, that is x is less than y. From there we are having this, that y minus x is a positive real number. Again, just like this one, the Archimedean property implies there exists a positive integer n such that n times y minus x is greater than 1. Okay. Thus, ny will be greater than nx plus 1. Okay. Now we are going to use exercise 543, where we proved that for any real number x, there exists precisely one integer n that satisfies, for which these inequalities are true. In the previous video, if you go to the previous video, you will see that we ended the video with that exercise. And in fact, this n is called the integer part of x and is denoted by this symbol. Okay, so we are going to now use that. Now, by exercise 543, and we are going to use this on the real number nx. That is, the integer part of nx is less than or equal to nx, which is less than the integer part of nx plus 1. Okay. Hence, nx is strictly less than integer part of nx plus 1. But now if we use the first inequality here, that is, if we add 1 on both sides of the first inequality, this will be less than or equal to nx plus 1, but then nx plus 1 is strictly less than ny. So this is less than ny. We thus have nx less than integer part of nx plus 1, that is less than ny. Since n is positive, we can now divide throughout by n. The inequalities will not get reversed. since n is positive, we have x less than, let me write it here, divided by n. The fact that n is 0 allows us to divide by n, and additionally, since n is positive, the inequalities don't get reversed. Thus, we have found the rational number q, which is this. Note that this is in fact a rational number because both the numerator and denominator are integers, such that x is less than q and q is less than y. So this completes the proof. Next, exercise 6, 546. Let x and y be real numbers. And let epsilon be a positive real number. Show that the absolute value of where is it? Absolute value of x minus y is strictly less than epsilon if and only if y minus epsilon is less than x, which is less than y plus epsilon. And that the absolute value is less than or equal to epsilon. Here we don't have the strict inequalities. Less than or equal to x, this is less than or equal to y plus epsilon. Okay. Let C be a real number. Now we want to show that both C as well as minus C are less than or equal to the absolute value of C. If C is greater than or equal to 0, then C is equal to absolute value of C by the definition of absolute value of a real number. On the other hand, if C is less than 0, then this is less than or equal to, or we won't have equality because we don't have 0. So absolute value of C is strictly greater than 0. This also we know, the absolute value of a real number is 0 by the very definition of absolute value, if and only if the real number itself is 0. So here, since C is non-zero, so its absolute value will be strictly positive actually. Thus, in general, C is less than or equal to the absolute value of C. This implies if in place of C we consider minus C. We can consider because that is also a real number. For that also this inequality will be true. But we know that the absolute value of minus C is the same as the absolute value of C. Okay, now we are going to use these inequalities to prove these claims. Now assume that this is less than epsilon. Okay, so let us first use this one. Then x minus y is less than or equal to absolute value of x minus y, which is, according to our assumption, less than epsilon. So here in place of C we are considering the real number x minus y, which implies x is less than y plus epsilon. Also, y minus x, which is minus of x minus y, that is also less than or equal to absolute value of x minus y. So here we are using this inequality. Minus C is also less than or equal to the absolute value of C. So this is less than epsilon. Y minus x is less than epsilon, that means y minus epsilon will be less than x. We have thus shown that y minus epsilon is less than x and x is less than y plus epsilon. So 1/2 of this statement is true. Now the converse. Conversely, assume that y minus epsilon is less than x and x is less than y plus epsilon. Then we have, okay, so from the first inequality we have this minus of x minus y, which is equal to y minus x, that is less than epsilon, and from the second inequality we have this x minus y is less than epsilon. Now since absolute value of x minus y is either x minus y or it's negative, and since both of them are less than epsilon, so the absolute value also will be less than epsilon. In fact, instead of just vaguely writing plus minus, let us properly write what it becomes equal to in each case. If x is greater than or equal to y and minus x minus y, if x is less than y, we have these inequalities imply this. So the converse is also true. One can similarly prove that this is less than or equal to epsilon if and only if this is less than or equal to x and x is less than or equal to y plus epsilon, which is basically just the same proof with the strict inequalities replaced by this type of inequalities. I need some ink. Then exercise 7. Let x and y be real numbers. Okay, show that x is less than or equal to y plus epsilon for all real numbers. Epsilon greater than 0 if and only if x is less than or equal to y. So this is one thing, and additionally there is another part also. Show that the absolute value of x minus y is less than epsilon for all real numbers epsilon greater than 0 if and only if x is equal to y. So these results will remind you of similar results proved. We have already proved where in place of real numbers we had rational numbers. Okay, so let us see the solution. So we prove this one first. If x is less than or equal to y, because we have if and only if, so we have to prove both the implications. Let us conclude the easier one first. If x is less than or equal to y, then obviously x is also less than or equal to y plus epsilon for every real positive epsilon. Conversely, assume that x is less than or equal to y plus epsilon for all real positive epsilon. Our claim is this, that x must be less than or equal to y. Suppose the contrary is true, I mean the other thing is true. Suppose y is less than x, then for this particular value of epsilon, x minus y divided by 2, this can be taken as epsilon because this is positive. From our supposition it follows that that is a positive real number. This epsilon also we should have this, that is our hypothesis should be true, x is less than or equal to y plus epsilon. In fact, let's just distinguish this epsilon because it's a particular epsilon by denoting it epsilon naught. But y plus epsilon naught is equal to y plus x minus y divided by 2, which if you take LCM and then do all the calculations, you will see 2y minus y, so this is x plus y divided by 2. Okay, and this is less than or equal to, am I doing it correctly, x plus y divided by 2. Okay, and this is greater than or equal to x. Why is it greater than or equal to x? Let me just see whether what I have got is correct or not. If I want a contradiction to appear here, then I must somehow contradict the supposition y less than x. So now I should have y greater than or equal to x. Oh, see, I forgot the entire thing. We are having this, so that means this should be greater than or equal to x. Okay, and this implies that x is less than or equal to y. Why? Because you see, you multiply on both sides of this inequality by 2, and that will give you x plus y greater than or equal to 2x, which implies y is greater than or equal to x minus 2x minus x. So that gives us y greater than or equal to x. So this is in direct contradiction to our supposition. This in fact the writing here has not been very good. We should start like this, but x is less than or equal to this, and then from this inequality we are concluding this. This contradicts our supposition. So the supposition is wrong. That is, we must have x less than or equal to y. So this completes the proof of the first thing. Now for this statement also we proceed similarly. Next, if x is equal to y, then the absolute value of x minus y is 0, which obviously is less than epsilon, for all real epsilon greater than 0. Conversely, we assume that the absolute value is less than epsilon for all epsilon greater than 0. We want to prove that x is equal to y. To the contrary, suppose x is not equal to y. Then for epsilon 1 equal to this, also note that since x is not equal to y, x minus y is a non-zero real number, so its absolute value will be positive. If you divide that by 2, that also is a positive real number. Epsilon 1, we are denoting that by epsilon 1. Also, we should have but the inequality so we now put the actual expression for epsilon 1 implies 1 is less than 1 over 2, which is not possible. Keep in mind that we have been able to cancel absolute value of x minus y from both sides, because this is positive. So our supposition that x and y are distinct is wrong. That is, we must have x equal to y. So that completes the solution. Okay. Next, exercise 8. So that was 7. Okay, this is the last one. Let an, where n varies from 1 through infinity, be a Cauchy sequence of rationals. And let x be a real number. Okay, so x be a real number. Show that if an is less than or equal to x for all n, for every n thing, for all positive integers n, then the formal limit of the sequence is also less than or equal to x. Similarly, show that if the other inequality is true, that is, if an is greater than or equal to x for all the indices n, then the formal limit of an is also greater than or equal to x. And hint is given, proof by contradiction. Also use proposition 5,4,14. That means the one which says that between two distinct real numbers there is a rational number, that one. To find a rational number between the formal limit of the sequence an and x, and then use proposition 549. Okay, so let us see. In fact, the solution will exactly proceed in this manner, the path laid out in the hints. Okay, so we are going to show this one, and we will we will mention that this can be similarly proved, which is true. We just need to show only one of them, so we choose to show the first one. So let a and b less than or equal to x for all n greater than or equal to 1. Our aim is to show that this is true. So let us choose let us assume that the other thing is true. Suppose the formal limit of an is greater than x by proposition 5414. There is a rational number q such that, because you see these are also two real numbers, say y and x, so between them there will be a rational number. This is greater than q and q is greater than x. Okay, now the first inequality implies this: 0 is greater than q minus limit of an, which is equal to, because q is a rational number, it equals the formal limit of the sequence, all of whose terms are equal to that same rational number, that is the constant sequence q q q q. And according to the definition of the operations in the system of real numbers, this is equal to the limit of the sequence q minus an. Okay, so we see that the sequence q minus an has a formal limit which is a negative real number. But now we are going to use these inequalities. Since we are going to use these inequalities, I am saying q is greater than x. Yes, since an is less than or equal to x for all n greater than or equal to 0 and q is greater than x, so each an will be strictly less than q. An less than x for all n greater than or equal to 1. This implies q minus an is it is a Cauchy sequence because it's the difference of two Cauchy sequences. One of them is an and the other is the constant sequence q. This is a Cauchy sequence of positive rational numbers. These inequalities tell us that all the terms of this sequence are positive rational numbers. Thus, now here this is the point where we are going to use proposition 549. Proposition 549 says that if we have a sequence of rational numbers, a Cauchy sequence of rational numbers where all the numbers are non-negative, then the formal limit is a non-negative real number. Here all the terms are positive, but positive means non-negative. So the formal limit of this also will be non-negative. Note that you cannot claim that since all the terms are positive, the formal limit also has to be positive. A counter example to that statement is this sequence. It's a Cauchy sequence of positive rational numbers, but the formal limit is 0, which is not positive. In general, it is non-negative. This is going to be non-negative, greater than or equal to 0, and which is in direct contradiction to this one, which is saying that the formal limit is less than 0. In fact, what is it that is being contradicted? These two inequalities cannot be simultaneously true because the order relation we have in the system of real numbers satisfies trichotomy, which says that for any two real numbers x and y, either x is greater than y, or x is less than y, or x is equal to y, and no two of these three statements can be simultaneously true. So that thing is being contradicted. This is a contradiction and proves that our supposition is wrong. What is it that this supposition? That is, we must not have this. So that means, again by trichotomy, this should be less than or equal to x, similarly, one can prove that if an is greater than or equal to x for all indices n, then the formal limit is also greater than or equal to x. This completes the solution, and the current set of exercises is over. In the next video, we will look at the least upper bound property that the system of real numbers has, and This is the main thing that distinguishes the real number system from the rational number system. So far, whatever we have seen about real numbers, they are also true for rational numbers. But in the next section, we are going to see that things differ, and that is the primary reason for constructing the system of real numbers. And after that, there is one more section in this chapter on real exponentiation. So then the chapter will be over. Okay, so we will see in the next video how one can use all the things in the system of real numbers to get that least upper bound property, and using that property we will show that the difficulties we had with the system of rational numbers, for example, the rational number system does not have any square root of 2, so those difficulties can be overcome. So with this I end this video here. So see you in the next video. This is me, Lucifer, from a mathematical room. Have a nice night.